Okay, let's get started. I hope background noise here doesn't affect you. Do you hear any background noise from my side? Okay, good, thank you. So today we're going to continue to talk about evolution of sun-like stars. So here, first, I want to start a few poll questions. After the sun exhausts the hydrogen in the core, what happens next? So please answer the poll on Zoom. Is it helium begin fusing into carbon immediately, or the core will contract, or core will expand? Okay, I'll end it now. So here is the result. Most of you chose B. The core will contract and heat up. That's the correct answer. Because while hydrogen is exhausted in the core, the fusion will stop, so that the temperature will drop and the pressure will become lower, so that gravity will win over the pressure, and so that the gravity will cause the core to contract. And as it contracts, some of the gravitational potential energy get turned into thermal energy, so the core heats up to a higher temperature. But again, it cannot start fusing helium yet, because helium fusion requires a much higher temperature, right? Because helium has much higher charge. So they cannot yet start fusing helium, but the temperature will start rising and it will contract. That's how temperature rises. At the same time, what happens to the surface of the star? Next question. Okay. Answer quickly, or I'll end the poll now. Okay, I'll end it now. Most of you got it correct. It's the last one is D, expands and cools. So that because the core is contracting, so that there's gravitational potential energy, and the region immediately surrounding the core will also contract, and it will also heat up, because the region that immediately surrounding it has to follow the core, right? And so it also heats up because of some of the gravitational potential energy gets converted to heat, and so that the region immediately surrounding the core will reach a temperature that allow fusion to start for hydrogen, because the core is exhausted of hydrogen, but the region immediately surrounding the core still has hydrogen. So those regions will start hydrogen fusion, so that you have gravitational contraction in the core and hydrogen fusion around the core, in a shell around the core. And so you have two energy sources. So actually the total luminosity actually goes up for the star. Actually give out the answer for the next question. And then so that there's too much energy being produced in the center. And because there's so much energy being produced in the center, but the heat transfer rate towards the outside is still slow. I mean, the outer part is still haven't changed, right? And so that it cannot transfer the heat out so much. So basically the center of the star will heat up so much. And because so that the pressure around it becomes high, and so it actually, because you trap too much heat inside, so that the star will have to expand to release that heat. So the star expands to allow the heat to go out, and then because it expands so much, that the surface temperature actually drops. So you have two energy sources, and because of the heat is trapped, so that it has to expand in order to let the heat go out. And that's why we call such stars red giants. And so the third question is, at the same time, what happens to the star's luminosity? I'm not going to set the poll anymore because I already gave out the answer. It will rise to higher luminosity because now there are two energy sources, the gravitational contraction in the core and also hydrogen fusion in a shell around the core. So these two energy sources will raise will make the total energy production faster than before. So it will give the star a higher luminosity. And because it expands, the luminosity increases and the radius also increases a lot. And so that the temperature has to fall to compensate, so that the surface temperature is falling, but the center temperature is rising. It's the surface temperature is falling. So the star becomes red because the temperature gets lower, the star looks, the spectrum will be at a redder wavelength, right? So that it will become redder in color, but higher in luminosity. So we call it, and also larger in size. So we call it a red giant star. So it goes to this part of the HR diagram. So that is what we talked about last time, that we have the red giant phase is the phase that is immediately after the mean sequence phase. So we have hydrogen to helium fusion in a shell around the core, and there is gravitational contraction in the core. So what event ends this phase? This is what we are going to continue to talk about today. So at the end of the red giant stage, the hydrogen fusion just continue to pile, hydrogen fusion in a shell just continue to pile more and more helium ash to the core. So the core contracts further and heats up further. And it causes the star to expand and luminosity increases, is what we have talked about already, and goes up that track until the point when the core becomes hot enough to start helium fusion. And the helium fusion requires a much higher temperature than hydrogen fusion. Hydrogen fusion requires 10 million Kelvin of temperature, but helium fusion will require 100 million Kelvin of temperature. And why is that? Because helium have higher charges, right? Because each helium nuclei have two charges, and so that if you want to fuse them together, you have to push the two helium nuclei towards each other, and you have to overcome the electric repulsive force between them. But because each helium nuclei has two positive charges, so that the force pushing them apart from each other is 4 times higher than the two hydrogen nuclei. So it's much harder to push two helium nuclei together. So that process is difficult, and so that is why it requires a higher temperature. It requires 100 million Kelvin for that to happen. But also helium fusion, you want to start helium fusion in the core, that process is actually not stable. So there was a question, so is the star hotter in the core but cooler on the surface? That's right. A red giant is hotter in the core compared to a mean sequence star, but it's cooler on the surface. It is hotter in the core, so there's actually higher energy production. So that's why its luminosity is higher, right? But because that the heat couldn't get out so easily, if the structure of the star doesn't change, if the structure of the star was still the way it was when it was a mean sequence star, then it does not allow the heat transfer to go out efficiently. So the star has to expand, basically make the outer regions less dense, so that it make the photons easier to go out or to scatter out. And so that's to increase the radiative transfer efficiency, so that the star has to expand. Because it expands so much, the surface temperature gets cooler than what it was on the mean sequence, but the center is actually getting hotter. And so it gets hot enough so it can start helium fusion. But starting helium fusion in the core is very different than starting hydrogen fusion in the core. Helium fusion in the right giant is actually not stable. Why is that? And previously we talked about hydrogen fusion being stable in the center of the sun, right? In the center of a mean sequence star. Why is hydrogen fusion stable? Because it was controlled by a negative feedback loop produced by gravitational equilibrium, right? Because so let's review that situation. In a mean sequence star, hydrogen fusion, why is it stable? Because if the fusion rate suddenly fluctuates a little bit higher, then it'll make the temperature higher, right? It'll make the pressure higher. So because pressure is balanced with gravity, and if the pressure in the center gets higher, it will expand the core a little bit. When it expands, the density, the temperature will drop. The temperature drop that reduces the fusion rate. So that basically that forms a negative feedback loop. So that you cannot go too high. The fusion rate cannot go too high or too low, or too fast or too slow. And it's basically controlled by this gravitational equilibrium. That's what's the situation in a mean sequence star. But this condition is very different in a right giant star. Why is that? Because in the core of a right giant star, there are actually two types of pressure that are supporting the center. Because the center has been compressed a lot compared to what it was. So remember, at the end of the mean sequence, the core started contracting, right? And the gravitational contraction is producing some of the energy. And that gravitational contraction process will compress the core by a lot. And so that the density in the core gets really, really high. And when the density gets really high, the second type of pressure starts kicking in. That is the electron degeneracy pressure. So it's not just thermal pressure that was supporting the star. It's actually two kinds of pressure supporting the star. The thermal pressure is the pressure that we are familiar with. It's basically our atmosphere pressure is the thermal pressure. And in a mean sequence star, the center pressure is supported by thermal pressure. But we talked about the electron degeneracy pressure once before when we talk about protostar, right? When protostar, in a very low mass protostar, it cannot start hydrogen fusion. And basically, if the mass of a protostar is smaller than 0.08 solar mass, its density, its gravity is not high enough to overcome the electron degeneracy pressures produced in the core of that protostar. And we talk about this phenomena. So that pressure is proportional to density. It has nothing to do with temperature. It's just proportional to density to the 5/3 power. Both of these pressures exist all the time. And in most of our daily situations, it's the thermal pressure that we can sense and feel because it is dominant. The density that we encounter in our normal life is just too low for electron degeneracy pressure to be noticeable. It does exist, but it's so small compared to the thermal pressure in most situations in our life. But in the center of a low mass protostar, or the centers of the core of a right giant star, the density is high enough that the pressure from electron degeneracy actually also kicks in. And just want to review, what is this electron degeneracy pressure? It's a pressure that is related with quantum mechanics. It's basically that you cannot put infinite number of electrons in a certain volume. You cannot compact them so much. And it's like a theater with a fixed number of seats, and you can only sit so many people. No two electrons can sit in the same seat or could be in the same quantum mechanical state. So that each electron has to occupy a separate state. This is called the Pauli exclusion principle. Because they cannot occupy the same state, so that if you have a limited volume, you have a limited number of these quantum mechanical states, just like a theater has a fixed number of seats. And so if you want to put more electron in there, you cannot. The quantum mechanical laws will not allow you to do that. It will prevent more electrons from being pressed in. So that works like a pressure. And that pressure has nothing to do with temperature. It only has something to do with density. So if temperature goes up, pressure stays the same. There's no expansion of the core. So there's no negative feedback loop that is formed. So in the center of a right giant star, because the pressure is partially supported by degeneracy pressure, that if fusion of helium starts, it will raise the temperature. And with the temperature getting higher, fusion rate will get even faster, right? So higher temperature makes fusion rate even faster, and that will raise the temperature even further, which makes the fusion rate even faster. There's no expansion of the core that try to reduce the temperature. So there's no control. So because of that, it actually have a runaway. You have a runaway process. It's just helium fusion gets crazy high. Helium fusion rate gets crazily high, and so basically it's like a bomb, like a helium atomic bomb. Actually, I mean, instead of a hydrogen bomb, now we actually have a helium bomb, because the helium fusion is not being controlled by this negative feedback loop. It can continue to raise the temperature and gets faster and faster fusion rate. And so this event, and because the temperature is so high, it will cause the thermal pressure to rise very suddenly as well. And so that the pressure gets so high, and it will all of a sudden becomes much stronger than gravity, because with pressures all of a sudden becomes much higher than gravity, then it will cause the core to expand. But it won't expand until the temperature gets so much higher and fusion rate gets so much higher, so that you all of a sudden you'll have a helium bomb that is composed of so much helium that is basically all the core is helium, right? And it's all of these helium all of a sudden starts fusion, and you will have an explosive process in the core, and the core will expand. When expanded enough that the density will drop, the electron degeneracy pressure will become less dominant than the thermal pressure. So that when the thermal pressure starts dominating in the process, then it will stabilize the core, so that you start having the negative feedback loop. Again, basically this helium, it's a runaway helium fusion process will explode the core, but it won't explode the star. The star, the outer layer of the star is still so massive. It's basically still pressing down toward the center, and the runaway helium fusion is not strong enough to destroy the whole star, but actually it will all of a sudden expand the core by a lot. And because it expands so much, the temperature in the core, in the shell also drops, and luminosity will drop. The star will shrink a bit, and the surface will get hotter. So it's like a helium bomb, and then you have a helium flash, like a hydrogen bomb. That now you have a helium bomb in the core of the star, and it's just that that fusion process is very fast. And then the core expands and it stabilizes the core. It becomes because the core expands and the temperature around the core also drops, so that the total energy production gets a little lower than the end stage of the right giant. So the luminosity drops, and the star also shrink a little bit, so that it moves to this region of the HR diagram, and the star enters a new phase. So that basically at the end of the right giant, we have onside of helium into carbon in the core, and then we start helium fusing star. So actually, I think I may have missed a few slides in the process. You can give me a moment. Yeah, so I did have missed a few slides. Let me actually use these to talk about that. Where did it go? Sorry, something is wrong with Adobe. So yeah, there was a question about why does fusion of helium into heavier element require higher temperature than hydrogen fusion. I told you it is because the helium nuclei have twice the positive charge than hydrogen nuclei. And here is the process. Yeah, this is explanation for that. I talked about that through the slide. And then here, this is the process of how helium is fused into carbon. It's called the triple alpha process. Basically, a helium nuclei is what we call an alpha particle. So helium, two helium nuclei can form a beryllium nucleus. Yeah, I will update the slides later so that you have the correct version. So two helium nuclei will form a one beryllium nucleus. But beryllium nucleus is not a stable one. It is very unstable. Actually, this process takes more energy than it gave out. But it can happen sort of for a short moment that the beryllium nuclei has a very short lifetime, so that you actually need a third helium nuclei to combine with the beryllium nuclei before it dies, before it splits again. Before this thing splits back to two helium nuclei, if we encounter some third helium nucleus, then these two can form a carbon nucleus. So actually, helium fusion directly into carbon in the overall process, because the beryllium one is very unstable and it has very short lifetime. So the overall reaction is effectively 3 helium nuclei to form 1 carbon nucleus. And then it emits some gamma ray radiation in the process. That's where the energy goes. So this is that process. And the energy released in fusing helium to carbon can be calculated using E equals mc squared. What is m in this equation? I didn't set up a Zoom poll for this, so you have to answer using the chat. Please make a choice for this one. using the chat window. Any other answers? Thank you. Okay, so a few you answered, so I will continue. Thank you for those of you who have answered. You all got it correct. It's correct choice is C. Wait. It is the mass difference of between 3 helium atoms and 1 carbon atom, because that this M is the mass difference before and after the reaction, not A or B or D. Okay, then this is what okay, let me just try to make sure this is fine. So we talk about the electron is packed as tightly as allowed by quantum mechanics. And so that, and how dense it is, it's actually 1 cubic centimeter would have a mass of 1,000 kilograms. So that was a density that is very, very high compared to water. This is a million times higher than the water density. So that density, electron degeneracy pressure is kicking in and helping to support the star. That when the density is low, that you can still put in more electron, but if the density is high, that you cannot push more electron in, so that it doesn't have that negative feedback loop. When the helium fusion starts, that it will just continue to raise the temperature until the core explodes. And then the density gets lower, so that the thermal pressure start to be the dominant pressure supporting against gravity. Then you set up the gravitational equilibrium again. But because the core expands so much, the temperature in the core and the shell will drop a little, and luminosity drops, star shrinks a bit, and surface gets hotter, so that it enters the helium fusing stage. Okay, now let's back on track about this. Okay, sorry about that. So this process, we have talked about the right giant phase, is much shorter process than the mean sequence lifetime of a star. The mean sequence lifetime of the sun is 10 billion years. The right giant phase only lasts about 1.3 billion years. And then the helium fusion phase is even shorter. It only takes 0.2 billion years for the sun. And so the reason is because helium fusion is much faster, right, than hydrogen fusion, and the luminosity is high, and it's very quick to exhaust all the helium fusion. So a structure of a helium fusion star is actually has 2 energy production as well. That in the core you have helium core fusion, but the shell that is surround the core is still very hot. It still had a higher temperature than what it was when the star was on the mean sequence, right? So that at that region, it is not hot enough to fuse helium, but it's still hot enough to fuse hydrogen, so that you will have helium core fusion and hydrogen shell fusion. And this helium core fusion will start to build up carbon in the core, and the hydrogen shell fusion will continue to produce more helium and adds those helium to the core. So what you have, what principal fusion reactions you have in this stage is you have 2 fusion processes going on. You have helium fusion into carbon in the core, and you have hydrogen fusion into helium in a shell around the core. So you accumulate carbon in the surface, and then accumulate carbon in the core, and then the hydrogen fusion in a shell just contribute to more helium to the core. Trinto asked, does the hydrogen shell go all the way to the surface? No, it doesn't go all the way to the surface. The surface temperature is only several thousand K, and that is not high enough for hydrogen fusion to start on the surface. Outside this hydrogen fusion shell, you still have a radiative core and a radiative shell and convective shell. So radiative zone and convective zone. And so on all the outer layers. The outer layers, their job is to just transport the energy from the middle to the outside. You don't have other, so it's still relatively, this hydrogen fusion is happening in the region that is immediately surrounding the core. And you don't have gravitational contraction in the core at this stage because it is, you have fusion there, so that is hot enough to produce pressure to support against gravity, so the core does not contract in this phase. So what is the event ending this phase? You could have guessed. You could guess it. What event ends this phase? It's just like the end of mean sequence, right? No, it doesn't start fusing silicon yet, but this helium fusing start is just like the mean sequence phase, except that mean sequence is doing hydrogen to helium fusion, and the helium fusing start is helium to carbon fusion, right? So this stage is ended by the exhaustion of helium in the core. So that you use up all the helium in the core. And then although that there is some hydrogen producing more helium in a shell around the core, that process is not fast enough, so that you basically exhaust the, I mean, you do produce some helium outside, but the temperature in the shell is not hot enough to start helium fusion, so that only in the core region that you can fuse helium into carbon. And at that region where it is hot enough to fuse carbon, you exhaust helium in that region. And when this is exhausted, what happens next? What happens after the helium is exhausted in a helium fusion star? Just like what happens at the end of a mean sequence star, right? When hydrogen fusion stops, the helium core will contract. When helium fusion stops, in a helium fusing star, the helium core will contract, right? Actually, sorry, not the helium core. It's now a carbon core, because helium have turned into carbon, and helium is exhausted in the core. So the core is completely made of carbon. And then when the core is completely made of carbon, it cannot start fusion the next thing yet, because if it wants to, it has to have much higher temperature for that to happen, right? You have to have much higher temperature for carbon fusion to happen, because carbon have much higher electric charge in the middle, in the carbon nucleus, so that it cannot start the next fusion yet. And so the temperature will drop when fusion stops in the core. And so that what is going to happen is that gravity will win against pressure, and it cause the core to contract. The carbon core will start to contract, but the temperature around the carbon core will get hot enough to fuse helium. So you have helium shell fusion around a contracting carbon core. But that's not yet. Around the helium shell fusion, we still have hydrogen shell fusion above that, right? And so that you have now 3 energy production sources: gravitational contraction of the carbon core, helium shell fusion, and hydrogen shell fusion. So it's like this. So you have a carbon core that is shrinking and turning gravitational potential energy into heat. You have helium fusing into carbon around it, and then you have hydrogen fusing into helium around that. So you have one contracting core with 2 fusion shells. So we call this double shell fusion star. So because now you have 3 energy production sources, you produce more energy than the helium fusing star, so that the luminosity of the star is going to rise. But again, immediately that those luminosity, this energy production cannot get out so easily out of a helium fusing star, because the energy, the outer layers always responds too slowly. The outer layers, their transparency, or you say their energy transfer efficiency was still what it was before, right? And so they were not able to transfer out so much energy that is produced in the center. And so basically, for a moment, it will trap this too much heat inside. If you trap so much heat inside, that will cause the whole region to expand. And until the outer region expands so much that they becomes less dense than before, then the photons can more effectively get out. So it actually causes the star to expand even more. So the star once again becomes a much bigger star. And that, yeah, this is 3 energy sources, and the outer layer expands again, and it becomes to have even brighter luminosity because there are 3 energy sources, right? So that's from the helium core fusion star, the star goes up on the HR diagram to even higher luminosity, and we now call it a red supergiant. And this is what we also call double shell fusion red giant. So the star becomes even bigger than what it was during the red giant phase. And so that we call a red supergiant. This is also a double shell fusion star, so that you have 2 energy production in shells, and then you have 1 energy production caused by gravitational contraction in the core. And so what event ends this phase? You please make a guess on that. What event ends this phase? Carbon to the next elements? Yeah, kind of, that's right. If the temperature can get hot enough, then you would continue fusing carbon into heavier elements, right? However, the sun is not massive enough to reach that temperature. What event should end the sun's red supergiant phase? At this point, that whether it ends in a carbon, what ends this phase actually depends on what kind of mass the star has. For our sun, the red supergiant phase will actually not end up in fusing carbon into a heavier elements. Some of you said supernova. No, not yet. I won't go into a supernova explosion yet. So what will happen is that if we want to fuse carbon into the next elements, it requires 600 million Kelvin, much higher than helium fusion into carbon. Helium fusion into carbon is 100 million Kelvin. But if you want to fuse carbon, you need 6 times higher temperature. But the sun's mass is actually not hot enough for that to happen. If we would not be able to reach that temperature, and what is going to happen is that this thing comes in again, electron degeneracy pressure. This is the enemy of gravity, right? Gravity is trying to compress the star even more so that the temperature can get high enough to start fusing carbon into heavier elements. However, there is this enemy of gravity that is called electron degeneracy pressure. This thing kicks in again because that you want to reach higher temperature, you have to make the center very, very dense. But the sun's gravity is not strong enough to overcome the electron degeneracy pressure. And again, it was due to the resistance of compressing more electrons into a limited number of seeds. The core becomes so dense that the electron degeneracy pressure is strong enough to prevent further contraction. And basically, as it continues to contract, at some point, that contraction just stops. That it cannot contract any further because the electron degeneracy pressure is too high. Remember that this I didn't show the formula here. That the pressure, that electron density pressure is proportional to density to the 5/3 power, right? So it actually goes faster than density. That if you make the density higher, the pressure goes up very quickly. And so if you just make the core denser and denser until the point when it is strong enough just to support the star. And that's the end of the story, that you cannot contract the core anymore. So for our sun, the mass of the sun is not sufficient for its carbon core to reach 600 million Kelvin, so that we cannot start carbon fusion in the center of the star. So the end of this is just the end of core contraction. So what will happen next? That the outer layers can continue doing fusion. So you can continue to pile more carbon onto the core, and the hydrogen into helium fusion can continue to put more helium. And so that you have this, you're making the core a little bit more bigger, but still that the pressure is sufficient to support the whole star. But also that during the red giant phase and the red supergiant phase, the star outer layers become so thin because it has expanded so much, right? The outer layers becomes a very, very low density medium. And because it's so thin that it's actually very easy to be pushed away by radiation pressure. Just remember that the center of the star is very, very hot, and all these luminosity is trying to get out, right? So there's a lot of light trying to scatter out of the star. So that effectively puts a lot of pressure on the outer layers of star. It's called radiation pressure. And also there is a stellar wind that actually can drive away some of the outer layers. And that results in substantial mass loss. By mass loss, we just mean the star is actually losing its mass. It's losing its outer layers by pushing them away. So the outer layers is being shed off by a star. So they are losing mass. Even during the red giant phase, our sun will lose a lot of our mass because it's become so big that the outer layers is so thin and very easy to push away. And when the outer layer is so far away from the center, the gravity also gets weaker, right? So it's easy to push those material away if there was enough radiation pressure. So a red giant will lose a lot of weight. So this red giant star says, I'm too fat, I need to lose weight. The red supergiant is saying, oh, you're not losing enough mass. I'm the biggest loser. So they will these two phases will both lose a lot of its mass. The outer envelopes are basically ejecting to the space, especially at the end of the red supergiant phase. That those fusion reactions around a carbon-rich degenerate core is actually not very stable. So that those processes can cause the star to expand and shrink for multiple times. And during that process, it will eject almost all the outer envelopes into space. And actually, it will form a planetary nebula in the end. So the star's outer envelope, everything around the carbon core will be ejected into space and form these beautiful nebulas called planetary nebula, or planetary nebulae in plural form. So why we call these things planetary nebula? They have nothing to do with planets. The reason they're called planetary nebula is because in the old days, when people look at these things using a small telescope, they cannot perfectly resolve them. So they look like a round disk, little round disk. But these are actually just expanding shells of gas from a dying star. And so that people saw that these things look like planets, so they gave them the name planetary nebulae, but they have nothing to do with planets. It's just the outer shells of the star being pushed away into space. And in the center of these planetary nebulae, you can always find something that is the left behind core basically a carbon core of the star that is just sitting there by itself, not doing anything. It's not doing gravitational contraction because the electron decentralized pressure has stopped that. And does it still have any fusion left? It may still have a tiny bit of fusion left on the surface, so that the surface becomes really, really hot. So these stars are really, really blue in color. Here is a picture of another planetary nebula. You can see it is fairly round because this is sort of the outer shells of the star being pushed away. And this is the life behind carbon core in the middle. So this is another example. You can see this process is not always the same in every star. Some stars can have more explosive processes than others, and the expansion of the outer shells are not always symmetric. It depends on how fast the star is rotating. It also depends on its magnetic field and how strong its magnetic field is. So all these things can impact how the outer shells are being ejected. But the same thing is that they're all ejected. All the outer shells in all these stars ejected. They're just ejecting in very different ways. You can see some of these stars make beautiful nebulas, right? They have very different shapes in each cases. But in the center, you always have a left behind carbon core. Here is another such planetary nebula. Also, there's a star in the middle. So somehow this star is ejecting most of its envelopes in the polar direction. Or perhaps it has strong magnetic field so that only material can go out in the polar direction. So these makes beautiful images of planetary nebula. And here another one. This one looks like the eye of a cat, right? It looks like a cat's eye, so it's called the cat's eye nebula. This one looks like one glasses. It's called the one glass nebula. So these beautiful pictures are all planetary nebula, and it's all indicating the end stage of a sun-like star. Basically, that you form a carbon core and then eject all the outer layers. The almost bare core is very hot, about 30,000 to 10,000, 100,000 K. The reason is why it is so hot is because there's a tiny bit of hydrogen and helium left on its surface, so that tiny bit can still fuse, can still have fusion reaction, so that gives it a very, very luminous, very, very hot temperature on the surface. And the ultraviolet radiation from the core will keep the nebula hot and glowing because the core is really hot, and so it gives out a lot of ultraviolet radiation. There's a question. There are two questions. One is, what about the black hole? They won't form black hole yet. For sun-like stars, the mass of the star is not heavy enough, so it will not continue to compress the star even more, so it cannot reach a density to form a black hole. And Trinto asks, sorry, could you please repeat why for the Sun nebula, the material is ejected in the direction of the star's poles? Actually, I don't know for sure what is the reason why material is ejecting the polar direction. My guess is that it has something to do with magnetic field, because it's easier for charged particles, for plasma to go along magnetic field lines than crossing them, right? So if a star have very strong magnetic field, I would think that it will cause the expansion of the material to be asymmetric because there's a preferred direction of motion. But that's just my guess. I have no idea exactly how they were doing this. You can look up. So that's sort of a more, it's an astrophysical question that you should ask astrophysics actually studying planetary nebula. I don't study planetary nebula myself, so I don't know the answer exactly. So here is a question for you. The gas that makes up a planetary nebula is hot and diffuse. What kind of spectrum does it produce? I don't have a Zoom poll, so please just type your answer in the chat window. What kind of spectrum would that a planetary nebula produce? That's right. The emission line spectrum, actually. I'm not looking directly towards the star. If you just look on a part of the nebula, then it is producing an emission line spectrum. And some of you answered absorption line spectrum. Of course, if you're looking directly towards the star, then it produces a continuum and the star is hotter than the nebula, you may have absorption line on top of that as well. But if you just look at the nebula itself, it has an emission line spectrum. The correct answer is C. Here is what a spectrum of a planetary nebula would look like. I have many emission lines that is produced by the gas in the nebula. The gas is heated by the star, by the central star, through radiation, so that it pumps some electrons to higher energy levels. And when those electrons come back to lower levels, they produce emission lines at certain wavelengths. So this is the phase that after double shell fusion right giant, this right supergiant phase, the star will eject its outer envelope and form a planetary nebula. And the core that is left, oh, actually, let's fill out the table here. From planetary nebula, is there any fusion reaction? There's a tiny bit left on the star's surface. And that is what makes the star look really hot. Basically here, the star surface, the star is basically just a carbon core left behind, right? Most of the outer envelope is rejected. There's no gravitational contraction because the electron degeneracy pressure have halted the gravitational contraction. And the end of this phase is indicated by the complete loss of the outer envelope. So what does star do? It will get very hot for a moment because that you have fusion on the surface of a star, so it looks really hot for a moment, but this type luminosity will drop quite significantly because that once that fusion reaction is gone, that you don't have any energy production sources anymore, right? So what luminosity will the star continue to make? The carbon core that is left behind is still hot for a long time, right? It was hot when it was inside the star, right? It was several hundred million Kelvin hot. So those energy that is stored, those thermal energy that is stored in the star has to be gradually radiated away, and the star will continue to cool down and form a white dwarf. Basically, the carbon core that is supported by electron degeneracy pressure is a white dwarf star. A white dwarf star is this kind of star that they're not making their luminosity through any fusion reactions. They're only bright because it was hot. Okay, because it was hot, because it takes a long time for them to cool down. So basically, at the end of this stage, it can be several tens of thousands of Kelvin. That is the temperature of the core, and then it's not making any more energy production. It's not producing any more energy. But it's radiate away the energy. So when some energy gets radiated away, the temperature will drop, and the star will decrease in temperature and also decrease in luminosity. The size of the star will not change at all because the size is basically controlled by how much gravity there is and how strong a degeneracy pressure it can have, right? So that the size of the star is basically fixed. Basically, you have perfect equilibrium between the gravity of the core and the electron degeneracy pressure. So that balance is perfect. And the stars keep a fixed size. And as the temperature goes down, luminosity drops. And so that it goes along this constant radius line in the luminosity versus temperature diagram. So this line is a constant temperature line, a constant radius line, right? And so it's all, this relationship is all set by the Stefan-Boltzmann law. Basically, the luminosity equals to the surface flux times the surface area, right? And surface area is now changing as with the surface temperature dropping, the luminosity is dropping. And white dwarf just continue to cool down. It's just basically, there's no more energy production. The star basically dies in this stage. So here is a text description. Its gravity is not strong enough to contract it further to reach the temperature needed for carbon fusion. No more activities on the star. It just continue to cool down by radiating away the energy. The star is hot, but very, very small. So it is very, very faint. Its luminosity is way lower than before. So this is the end of a sun-like star. This is basically the corpse of a star. It's the dead body of a star. The white dwarf, we call it a white dwarf in this case. There's no fusion, there's no gravitational contraction. What event ends that phase? That phase does never end. It's just a dead star. Keep its size and continue to cool down until it reaches absolute zero temperatures. And this is going to last a long, long, long time because there's so much heat that is trapped. It will take forever for it to reach a very low temperature. But it will last basically forever. There's no end to this phase. So this is the end of a star's life for a star that has a mass about the size of the sun. And so we have observed these white dwarfs in the universe. For example, one of the brightest star in the sky beside the sun is called Sirius, right? The brightest star at night is Sirius. And Sirius is actually a double star. It has a small companion, and that small companion is actually a white dwarf. So here is an image of Sirius. This is the primary star, very, very bright and blue, a mean sequence star. And then it has a companion that is a white dwarf. So this companion star is, it's a white dwarf. It's very, very small, and so it's much smaller in luminosity compared to the primary one. You can also find lots of these stars in any star clusters because star clusters are old. So some of those stars has died away and they have formed white dwarfs. For example, many of these globular clusters are older than 10 billion years. So only in these old globular clusters, you can find white dwarfs because it takes 10 billion years for the sun to evolve into a white dwarf, to evolve out of the mean sequence and then go through the red giant phase and the helium fusing phase and the red supergiant phase to form a white dwarf, right? So only in these old globular clusters, you can find these white dwarfs. Here is a picture of that. If you zoom in a tiny region of the globular cluster, you see many bright stars, but you see many of these much, much fainter stars compared to the other mean sequence stars. These are the white dwarfs. White dwarfs, the reason we call them dwarfs is not only because they are tiny, but also because they are very, very faint in luminosity. Because the core is so small that even though it have a surface flux that is similar to the sun or hotter sometimes, but the surface area is so tiny so that luminosity is so small compared to the sun. Does this mean that that globular cluster is very old? Yeah, this means that this globular cluster must be more than 11 billion years old, so that sun-like stars have already died away into these white dwarfs. And for most of these other brighter stars, you can see they must be lower mass than the sun. That's the situation. So although they look bright, they're not as massive as the sun either. So because the sun-like star, some of these sun-like stars have turned into white dwarf. all these stars will eventually turn into white dwarf as well, but they haven't reached that stage yet. So the star at a lower mass than the sun will continue to evolve for longer periods of time, but they eventually will also reach the white dwarf stage. Basically, everything that is less than 2 times the mass of the sun will become a white dwarf in the end. And this is the overall table that summarizes the life cycle of sun-like stars. And you can see we go through protostar stage, mean sequence, red giant, helium fusing star, red supergiant, planetary nebula, and white dwarf. So these 7 stages. And you can see that in many of these phases, you have gravitational contraction in the core, in the protostar stage, in the red giant stage, in the red supergiant stage. And then this shows you what fusion reaction is going on. When it is not having a core contraction, it always have a fusion in the core. But when it is having core contraction, it doesn't have fusion reaction in the core, but only in shells. The red giant phase is just 1 shell fusion. The red supergiant phase is 2 shell fusion, double shell fusion. And then you can see here is there's 2 onset of fusion. At the end of protostar, the onset is the onset of hydrogen into helium fusion. At the end of red giant phase, it's the onset of helium into carbon fusion. But then carbon fusion cannot start. Carbon fusion into more heavier elements cannot start in sun-like stars because the mass is not high enough. Okay, so what will happen to the Earth when the sun becomes a red giant? That's an interesting topic, so let's review this a little bit. So here, what I'm showing you is the radius of the sun as a function of time, as a function of its age. So this is from the 0th age into 10 billion years. And this stage is basically the mean sequence stage. At the beginning, this very beginning part is the protostar stage. It lasts a very short amount of time, but the sun spends most of its time on the mean sequence. Its radius changes very little. It gets a little bit bigger over the 10 billion years, but not very much. And then all the later stages are much faster compared to the mean sequence lifetime, so that you can see in the horizontal axis, we actually have to expand the axis, we zoom in on the axis. We have to zoom in on the axis in order to reveal those stages. So this is the red giant stage that the star gets much, much bigger until the radius becomes like 200 times bigger than it is now. And then you have the helium flash. This is the runaway helium fusion that starts the helium fusion in the star. And then at that time, when the helium flash causes the core to explode, the total energy production actually drops down. And also the radius of the star gets smaller. And this is the helium fusion phase. And over the helium fusing phase, it is also roughly stable in its size. And at the end of that, you reach the red supergiant phase, the star becomes large again. And also at the end of the red supergiant phase, it will not be very stable. It will expand and contract because it's going to be pulsating. We call it thermally pulsating star, thermal pulses, just because the energy production in the center is so high and the outer layers are so thin that the energy transfer rate and the energy production rate are not regulated so well, so that the star can pulses, expand and shrink in multiple stages. And this is also the time when it is shedding most of its mass and form a planetary nebula until and when the outer layers get ejected away, the star will become much, much smaller than before, and so transitioning to a white dwarf. we are actually in danger. If the sun expands into a right giant, it will actually become much larger than before. But also our orbits will be affected. Actually, I shown on this previous figure, this line is the present radius of the Earth's orbit. You can see that when the sun becomes a right giant star, the size of the sun almost reach the size of the Earth's orbit, right? So that does that mean that the Earth will be going around the sun on its surface? That not exactly the case, because as the sun is losing some of its mass during the right giant phase, the orbits of the planets will also be affected. When the sun goes into a right giant phase, it will lose about 25% of its mass. 25% of its mass will be ejected into space. And loss of so much mass will weaken the sun's gravity. So planets will move further away from the sun. Here is what it looks like. So here is the sun, here is Mercury's orbit, here is Venus' orbit, and here is Earth's orbit. And this is the current orbit of the sun. When the orbit of the planets around the sun. When the sun becomes a right giant star, it will expand a lot and it will reach almost to the size of the Earth's orbit. But during the same time, the sun is also losing its mass. So the Earth's orbit will become bigger, or orbit will be expanded. So this is after the sun loses its mass. This is where Mercury's orbit would be. This is where Venus' orbit would be, and this is where Earth's orbit would be. We'll still be safe. Kind of not being eaten by the sun. Will not be enveloped by the sun. Will still be out. The Earth's orbit will still be outside the sun, but the sun is getting is going to eat Mercury in it. So basically, it's going to completely engulf Mercury inside. But the outer envelope is not big enough to reach Venus orbit or the Earth's orbit. So most planets will still survive, but at the same time, the luminosity of the sun is going to be so much higher. This plot shows you how luminosity of the sun will evolve with time. Again, this is the mean sequence stage. The luminosity of the sun is roughly stable. It's not perfectly stable, but it's almost the same. And then in the right giant phase, it gets much higher, and then it reduces during the helium fusing star, and then it gets higher again during the right supergiant phase. And when it transitions to a white dwarf, it drops significantly to much lower luminosity. So because its luminosity becomes so much higher, that that the temperature on Earth will be much higher. There's a question, what is the difference between this graph and the one before? This graph was showing luminosity changes. The previous one was showing radius changes, and looks similar, but the Y scale is very different, right? This is radius. You can see radius goes from 1 to about a few hundred. So the sun will become about 200 times larger than what it was. And in this picture, this shows you luminosity. You can see at the end of the right giant phase, the luminosity will be about 3,000 times more luminous than today. Because of that high luminosity, it will cause the Earth's surface to be really, really hot. About 3 to 4 billion years from now, even before the sun finishes its mean sequence lifetime, the temperature on Earth will be so hot that the oceans will actually boil away. And when the sun becomes a right giant star, the Earth's surface temperature will be about 1,000 K. And that is certainly not a situation that we can survive in. So we actually need to move further away from the sun to avoid being extincted by the sun. And so this is the sort of the story. This is the setup of the sci-fi novel called The Wandering Earth, and also made into a sci-fi movie that came out a few years ago. And that was a fantastic movie. I really love it. If you haven't watched it, I recommend you watching it. It is describing what will happen, how we can deal with it at the end of the sun's mean sequence lifetime, if the sun becomes a red giant, what do we do, right? In the movie or in the novel, people on Earth came up with this idea of put many engines on Earth and propel the Earth away from the sun and to go to another star, to go to the Proxima Centauri, so that we can go orbit another star. But so they were basically taking Earth as a spaceship and driving Earth away from the sun. So that was a pretty good movie. So that's it. That is summarizes the low mass star evolution. And then next we can talk about high mass star evolution. So this is the process of low mass star evolution. I'd like to take a short break and then restart in 5 minutes. We'll take a short break and restart in 5 minutes. 3:45 or 4 minutes. Okay. Okay, let's get started again. So now we have talked about evolution of low mass stars. We are going to talk about evolution of massive stars. As you can see from this picture, this is going to result in a much more splendid ending. And that is a supernova in the end. The post-mean sequence evolution of a star depends significantly on its mass. And as I said before, we have stars into 3 categories: low mass stars, intermediate mass stars, and high mass stars. We looked at low mass stars, and they will end up as a white dwarf. Next, we are going to look at high mass stars, so stars that are more massive than 8 solar masses. And what kind of star would that make? What kind of ending would that make? In a high mass star, the situation is quite a bit different. After the core hydrogen is exhausted in the mean sequence, the initial part is very similar to a low mass star. The core contracts and heats up. So you have gravitational contraction. Fusion of hydrogen will start in a shell around the core, and star will expand but remain roughly the same luminosity. This is because the star is already very high luminosity to start with, and so that after it increases the gravitational contraction, hydrogen fusion, it will actually not expand very much. It will not, the temperature cannot get hotter by law, so that the luminosity is roughly the same. The star expands but remains roughly the same luminosity until the core reaches the temperature for fusing helium. So this is a sort of very similar process as before, but because that the star is much more massive, the center part is actually not as dense as a star like our sun, so that you don't have electron degeneracy pressure kicking in yet. So you can just peacefully start the helium core fusion in the core, and then enter helium core fusion plus hydrogen shell fusion in a peaceful way without a helium flash, right? Without going through that unstable helium flash process. So, and then once you have this process, you basically have a helium fusing star. And then the next stage is that when the helium core is exhausted, you again have core contraction and heats up, and fusion of helium stars in a shell around sorry. Right, fusion of helium stars in shells around the core, and also there's also hydrogen fusion in a shell around that. And the star will again expand but remain roughly the same luminosity until the core reaches a temperature of fusing carbon. So you have carbon core fusion plus helium shell fusion plus hydrogen shell fusion. And then once you do that, the star will shrink back again. And then next thing is that you just replace these red words in this process. And now the top is becoming, you exhaust carbon in the core, and the core contracts and heats up. And then fusion of carbon can start in the shell around the core, and star expands but remains roughly the same luminosity until the core reaches a temperature for fusing oxygen. So oxygen core, you have oxygen core fusion plus 3 shell fusions. You have just basically you go through all these elements and build higher and higher, heavier and heavier element in the center. What form is the carbon in the core in? What form of carbon? I'm not sure I understand your question. What kind of state of matter is that? It is a hot plasma. The carbon is basically completely free from the electrons, so it's just carbon nuclei and free electrons, and so it is still a plasma, and the density is high, but not high enough to reach the have significant electron degeneracy pressure. So it's just like the center of the sun. It's the hydrogen and helium plasma, right? And in the center of the carbon core star, it's just that the temperature can reach high enough to fuse the next element. And what the next element would be, it will be oxygen. What that process is carbon combining with helium to form oxygen. And then oxygen can combine with helium to form neon, and neon can combine with helium to form magnesium. So you can see that all these elements that are basically multiples of the helium nuclei. They can all be formed in the center of the stars. And when you have carbon meeting oxygen, you can also form silicon, and oxygen meeting oxygen, you can form sulfur, and silicon come together, they can form iron. So all these nuclear fusion processes will go on in the center of the star. What was the star do on the HR diagram? Will actually go back and forth for many times, right? When the core fusion stops, it goes to the right, it expands because it has gravitational contraction in the core and then some shell fusion around it. And when it gets to become a red giant. And then when the core gets hot enough to start the next fusion, it come back to this stage. So this is the helium fusing star with a hydrogen shell. And then when the helium is exhausted in the core, it goes to the right again to become a red supergiant, which is that you have gravitational contraction and 2 shell fusion. And when the carbon fusion stars in the center and to come back again, so that you can see some of these stars, they can go make multiple trips back and forth and to fuse next heavier elements, so that it basically forms an onion-like structure in the center of the star. That you have hydrogen shell fusion in the outer part, you have helium shell fusion inside, you have carbon shell fusion around that, you have oxygen shell fusion around that, and silicon shell fusion around an iron core. So basically you start accumulating iron in the middle. And then this iron core will get denser and denser. However, you cannot fuse iron into any other things. Fusion in the core will stop eventually when the core is made of iron. Because of fusion of iron into heavier elements does not release energy. Instead, it actually has to take energy to happen. So that means that you cannot make more energy through nuclear fusion. so that you don't do that. Why is that? Why can't we fuse high iron into heavier element and still produce energy? And to understand this, this is actually a very important concept, is that we have to understand how the energy is actually produced in nuclear fusion or nuclear fission. In fusion or fission reactions, the total number of nuclear particles has to stay fixed. It remains unchanged. What do I mean by nuclear particles? By nuclear particles, I mean protons and neutrons. Basically, the total number of protons plus neutrons have to stay fixed. When you have 4 hydrogen forming into 1 helium, 4 hydrogen has 4 protons, and 1 helium has 2 protons and 2 neutrons. 2 plus 2 is 4, so that at the beginning you have 4 nuclear particles, at the end you have 4 nuclear particles. This number does not change. When you turn 3 helium nuclei into 1 carbon nucleus, 3 helium nuclei has 6 protons and 6 neutrons, so total 12 particles. And 1 carbon nucleus also has 6 protons and 6 neutrons, so also 12 nuclear particles, so that the total numbers did not change. But how is energy released? Energy is released because the end product is lighter in mass than the total mass originally. So that if you calculate the mass per particle, it is always decreasing in the process. Basically, you take the total mass divided by the number of nuclear particles. That's give you the mass per nuclear particle. That mass per nuclear particle is decreasing in all the fusion processes. And because of that mass is reducing, there is some mass surplus. And that mass surplus is radiated away in energy through E equals mc squared. And that is how energy is released. So in order to have you have nuclear fusion releasing energy, you have to reduce the mass per particle. So hydrogen have a very high mass per particles. When it goes to helium, it can reduce a lot. This is process that produces energy in the sun. But iron has the lowest mass per particle among all the elements. It is a very special element. It has the lowest mass per particle. Basically, you can say it is the most stable elements ever. So that all the elements lighter than iron can release energy by fusing into heavier and heavier elements until iron. And all the elements that are heavier than iron can release energy through nuclear fission. What is nuclear fission? Meaning that a heavier nucleus breaks into multiple smaller nuclei. And in that process, they will also reduce the mass per particle. And so that they can also release energy through that process. But iron is the most stable one, so it sits at the bottom of this curve of the mass per nuclear particle versus the atomic mass, basically the number of nuclear particles in the horizontal axis. And iron has a value of 56, and this it has the lowest mass per particle. So it is most stable. You cannot get more nuclear energy out of iron anymore. So if you force 2 iron nuclei together to make them fuse into heavier elements, it actually does not release energy, it actually absorbs energy. It actually takes energy for that to happen. There's a mass deficit for that. So it has to absorb energy. And so this process cannot sustain itself, that you cannot have nuclear fusion anymore when you have an iron nuclei. But heavier than iron, you can get energy production by nuclear fission. This is what happens in an atomic bomb or in a nuclear power plant. But with iron, you cannot get any more nuclear energy out of it. So what happens when an iron core is formed in the center of a star? The iron core will contract. It will continue to have gravitational contraction until at some point the electron degeneracy pressure kicks in. However, the gravity of these massive stars is so strong that electron degeneracy pressure cannot stop the contraction. Gravity keeps compressing the core until the density reaches a limit that electrons have nowhere to go, that the electron degeneracy pressure can continue to get higher and higher until a point where there's just really nowhere to go, but this gravity is still strong. There's a limit of how much electron density pressure can be produced. Basically, electrons cannot get faster than the speed of light. And so that if you are trying to push more electrons into a fixed volume, electron has to go faster and faster. And eventually some electrons are approaching the speed of light in their velocities. And that's just not a sustainable process because it cannot exceed the speed of light. So basically there's a limit there's an upper limit of how high the electron degeneration pressure really can be. But in these massive stars, the gravity is just so much stronger than the maximum electron degeneration pressure there can be. So electron has nowhere to go, and they're basically pushed into protons. Electrons get pushed into protons. When they do that, they actually form a neutron and a neutrino. So electron combining with a proton and form a neutron. So all of a sudden, in an instant, electrons combine with protons to form neutrons, and the electron degeneration pressure just completely vanishes all of a sudden. And so that was a really sudden event. The whole star all of a sudden contract into a very, very tiny thing. And you release a huge amount of energy in that process. And this energy is so huge, it explodes the whole star. The whole star explodes in a supernova explosion. So this is one of the kind of supernovas that we can have in the universe. That is because one iron core gets so dense that the electron degeneration pressure no longer supports against gravity. The electron gets pressed into protons, and all of a sudden the pressure vanishes. The core contracts to a really, really tiny size, completely made of neutrons, and that is called a neutron star. So basically, all of a sudden, the core contracts into a really, really tiny neutron star, and all the outer envelopes just completely lose their support, and all the outer envelopes just rush in toward the center, towards a really, really hard neutron star. So the core is about a solar mass in this process, and core collapse stops when it is about 10 miles in diameter. So all of a sudden, the star shrinks from thousands of kilometers to the size of about 16 kilometers. And then the neutron degeneration pressure will hold it against gravity. Neutron degeneration pressure is much stronger than electron degeneration pressure, so you can hold it against gravity. But it is so dense and so hard, it has a really hard surface. A material from above just lose support in an instant and fall down towards the center. And so you have a very massive core. Okay, if the star was even more massive, if the core is much more massive than a solar mass, then even neutron degeneracy pressure cannot resist the crush of gravity. The core can become a black hole in an instant. So it really depends on how much mass is left in the core at the end. If it's just about the solar mass in the core, not the whole star, okay? This whole star is much more massive than the sun. But the core, if the core itself, just the core part is about a solar mass, then it form a neutron star in the middle. But if the core is more than 3 times massive than the sun, then it will form a black hole in an instant. But we'll talk about neutron stars and black hole in a later lecture. But let's talk about the supernova explosion for a moment. So that in most cases, you form a neutron star in the middle, and so it has a really hard surface. All the material from the top will rush in towards the hot surface, towards the center. And so it's like the material rushing in, and they will bounce back on the just formed neutron core, and they will hit a hard surface and then bounce back. Just like if you have I used to do this demo of having a ping pong ball on top of a basketball, and then I release both of the things at the same time to the bounce on the floor. The basketball will bounce back, but the ping pong ball will shoot up really, really far because the outer layers is less dense, right? When it's rushing in towards something really dense and massive, all all the bounce back energy will be translated to the outer layer, so that the outer layer will go out with really high speed. So that's one mechanism that we think that is causing supernova to explode. But actually, this is probably the wrong picture. This was originally thought to be the case. Conservation of momentum and energy, yes, that is because of the energy and momentum is conserved. So most of the energy actually get carried by the outer layers outwards. But that actually could be the wrong picture. We don't know really exactly how supernova exploded, but we think the more correct picture is actually because of the huge neutrino flux that is formed when the electron gets compressed into protons. When electron gets compressed into protons, you form a neutron, but also a neutrino. So a solar mass of protons combining with electrons is going to give a huge amount of neutrinos. All these neutrinos has to go out, but the star in the middle of the star is very dense. And so even though neutrino is very antisocial, it doesn't like to interact with other particles very much. It is still a small fraction of those neutrinos will still run into those nuclei, and actually will push the outer envelope out. So all the material from rushing in, and the neutrino flux runs into it and produce a shock wave through the material and eject it outward with huge velocity. So this is what can explode a supernova. This is how there's actually multiple kinds of supernova. This is only one kind of supernova that can happen. It is basically the end of a massive star. It forms a neutron star in the middle, and the outer envelope gets ejected. And we observed one of these supernova in the Large Magellanic Cloud, which is a small satellite galaxy just outside the Milky Way, in the year 1987. In the February 1987, in the southern sky, a star all of a sudden brightens up to be visible almost to the naked eye, and it is so bright that it's a supernova. It's a supernova that exploded. It's a massive star that reaches its end of life in the galaxy called Large Magellanic Cloud. In our Milky Way, we haven't had any of these supernova observed since 1604. For about 400 years, we haven't had supernova of this kind in the Milky Way. We expect something that will happen, but maybe it's in a faraway part, in the opposite part of the Milky Way that we didn't see, or that we're just unlucky that there hasn't been a supernova recently. I mean, we should be seeing one in the future. I mean, sometime in the future, we don't know. It's we have to wait. On average, a galaxy, it takes about 100 years for a galaxy to have a supernova. So we are kind of overdue for that. So this is a picture of a region of the Large Magellanic Cloud. You can see there was no star in there. And then all of a sudden, a star brightens up to be as luminous as the whole galaxy. So a star's luminosity in an instant, when it is doing a supernova explosion, its luminosity can rival the total luminosity of a whole galaxy, which basically rivals hundreds of billions of stars. And during that supernova 1987, we have observed the neutrinos from that supernova. Neutrinos were actually detected first before the supernova was discovered in visible light. Because when the light first brightens up, we didn't see it immediately. But neutrinos was detected first. Neutrinos have very little mass, so it travels at nearly the speed of light. So it reaches us at the same time as photons reach us. And there are several neutrino detectors, and they all, in the world, they all detected these neutrinos. A Japanese one, an American detector, and a Russian detector, they all detected neutrinos. In total, we detected about 20-some 24 neutrinos coming from a supernova. Previously, all the neutrinos we detected was all coming from the sun. But this was the first time neutrino from a supernova was detected. It confirms the theory about the core collapse as the beginning of a supernova explosion. And the energy output of a supernova is very high. The total energy that is emitted in 1 second is comparable to the total energy emitted per second by all normal stars in the observable universe. So it is really, really bright for a moment, for that 1 second, okay? And most of that energy is actually not in terms of light. Most of that energy is in the form of neutrino flux. About 1% of the energy is in terms of the motion of ejecta. So basically the envelopes that is exploded, that mechanical energy carries about 1% of the energy. And what we see in visible light, what makes the star really, really bright, is only less than 0.01% of that total energy. So even it is only 0.01% of the total energy, it can make the star as bright as a whole galaxy. So supernova is among the most powerful explosions in the universe we know of. It's just very powerful because of the electron combining with photons in a core collapse of a more massive star. So after several years, after about 16 years since 1987, if you observe that region of the sky again, the supernova have faded, but they leave behind all these beautiful envelopes of the star that was ejected. So this is the envelope of the star that is pushed out, and you can still see that they're still hot, and we can still see them, but the star itself is gone. In Chinese history, we have observed many of these supernova, and one of the famous one is observed in the Song Dynasty in 1054 AD, and we have extensive record of the supernova in Chinese history books. And it will happen on July 4th, 1054 AD. And in the books, they write with large, many words about the supernova. It was visible at night for 2 years. Basically, it was so bright. This supernova happened in our Milky Way, not in another galaxy. So it was much more nearby. So it was so bright, it was brighter than Venus. And it was visible during the day for 23 days. So basically, that even when the sun is out, you can still see the star. That's just how weird that is, right? Just think about how weird that is when the sun is out. You can see a bright star in the blue sky. And that was a supernova that is in the Milky Way that is not too far away from us, about 6,000 light years away from us. It's very nearby in terms of astronomical distance. And so it is so bright, it was visible for months, visible during the day, and visible at night for almost 2 years. And I leave behind this beautiful nebula today that in that direction. And we now know this nebula is still expanding with some velocity. You can actually measure its expansion velocity using Doppler effect, and you can also measure how big it is. And if you use the distance divided by the velocity of the expansion, you can actually figure out how long ago the nebula exploded, right? And it exactly matches about 1,000 years ago. And this matches to the Chinese record of this supernova explosion. So we figured out this supernova is indeed this the progenitor events of this nebula that is left behind. And here is a picture of the nebula that in the middle, it indeed have a neutron star. And that neutron star, we can actually detect it through its radio emission. It sends regular pulses, and it's actually also called a pulsar. We'll talk about these things in the future. And then we can see that that star is a very young neutron star left behind, and all these beautiful colored filaments are the envelopes of star that was pushed out by the explosion event. So that is a supernova remnant, and there's many other supernova remnants in the universe. So here are some examples of that. Sometimes if the star is really massive, it doesn't leave behind a neutron star, it could leave behind a black hole. We actually talk about that in the next lecture. And so in the supernova explosion process, it will also make heavier elements, right? Because the explosion process is very hot and is a hot plasma, then actually you have plenty of energy to make other kind of elements. So that you not only produce a lot of iron in the process, you also produce a lot of nickel, and also elements heavier than iron can be made in the process of a supernova explosion. So a lot of elements on Earth that we use as minerals or materials, they actually come from supernova explosions. So we know that carbon in our bones, oxygen we breathe, they come from nuclear fusion in stars. But some of those also come from supernova explosions. So we are not only the children of fusion of stars, but we are also children of supernova remnants. And the sun, the solar system is very rich of these heavy elements. And the reason is that the solar system, the sun, is formed in a previous supernova remnants. That when a previous supernova exploded, it expelled these elements into space, and then formed those elements, the solar system formed. So we are actually made of not only material fused in the center of stars, but also made of remnants from supernova explosions. So you can see that this is iron in the middle of the periodical table. This is the most stable elements, but there are actually many other elements that are formed in the supernova explosions, and even though they have they're less stable than iron, they can be formed in the supernova explosions. Okay, that's the end of the lecture. I will continue a little bit about this in the next time, and then talk about the dead body of stars, white dwarfs, neutron stars, and black holes next time. Thank you. That's it for today. Bye-bye.
Bye-bye. Thank you.
Bye.
Thank you. Bye-bye.
Yeah, someone have a question? Yeah, go ahead. The format of the final exam is going to be very similar to the midterm, so don't worry. All multiple choice questions. I think probably no long answer questions, just multiple choice. Okay. Oh, what past paper finals? from UGEB 2401? That was from your seniors. Look at some papers from years past, library website. Okay, it's different. I'm not teaching exactly in the same way as before, so that the final exam is not the same. Okay. Thank you. Bye-bye.